Hello everybody, welcome to this class. In this class we are going to be talking about capacitors. This class we are going to talk about capacitors, right? It's called capacitors. So before we begin to dive into a capacitor, let's try to understand the meaning of a capacitor. Let's try to define the meaning of a capacitor. A capacitor is an electrical device, right, that is used in storing charges. A capacitor is an electrical device that is used in storing charges. How it works is that we have two plates that is separated by dielectric, right? The dielectric can be air, can be rubber, but a dielectric is an insulating material that doesn't conduct electricity. So in this place now, one side they have two plates. One side is connected to a positive voltage, and the other side is connected to a negative voltage. So how this happens is that when both of them are separated, there is an electric potential in between them, right? When both of them are separated, we have two plates separated by a distance, and that distance is by dielectric distance, right? Means that this distance there is no connecting material between them that can conduct electricity. So this positive voltage, you have charges, this side we have charges, and there will be a feed between them. Since we have positive and negative, there will be a feed between them, right? So that feed, even if the voltage is off, that feed is still there. Are we getting it now? That feed now stored as electric potential. When you now connect this to another source, that electric potential will continue to do work in form of voltage, right? So that is how it stores charge. So capacitors store charges in form, as capacitors store electric energy in form of charges, while battery store electric energy in form of chemical energy. Alright, so capacitance of a capacitor. A capacitance of a capacitor. Capacitance of a capacitor is the ability of a capacitor to store charges, right? So that is the charges that will be stored when a certain voltage, let's call this VAB, is applied. So when I apply a voltage VAB, how much charge can that capacitor store? It's called capacitance of a capacitor. Capacitance is measured in farad, but commonly it is measured in microfarad, right? And you know that 1 microfarad is 10 raised to power minus 6 farad. So in case you see this in calculation, this is how it goes. Now let's drop the formula for types of capacitor. We have different types of capacitor. The first one we talk about is a parallel plate capacitor. Parallel plate capacitor. Parallel plate. What is a parallel plate capacitor? A parallel plate capacitor simply means two plates, right, that are of flat surface, two flat surface plates. This is what it means by parallel plate capacitor. One we have minus, one we have plus. Without wasting time, the formula for calculating the capacitance of a parallel plate capacitor is given by C equal to K epsilon naught A all over D. This is the formula for calculating capacitance of parallel plate capacitor. Where K is the dielectric constant, A is the constant of permittivity, which is 8.85 times 10 to the power minus 11. A is the area of the plate, right? Since both plates have the same area, just take one of the plates, the area of the plate, and D is the distance of separation. C is the capacitance measured in farad. Are we getting it now? The next type of capacitor we are going to talk about, is quasi-cylindrical capacitor. This type of capacitor is very common in industries, right? Things like when you use things like fans, it's very common. It's called coaxial cylindrical capacitor. Coaxial cylindrical capacitor. So this capacitor, like I said, is very common in industries, right? So it's like a cylinder that's round, but inside the cylinder we have the internal external diameter, right? So we have internal diameter here. This internal diameter is where the dielectric is. We feed this internal diameter with dielectric, right? This external diameter here are the materials that we use. So from this hollow to the end is big B, and from this hollow to the end is big A. That means from this side to the end, to this small place to the radius is small a and is small b. So the capacitance of this capacitor is given by C is equal to 2 pi A naught L all over the lane natural logarithm of B over A. That's just it. Simple as ABCD. The next type of capacitor we'll talk about is capacitance of isolated conducting pair. Capacitance, right? Capacitance of isolated conducting pair. The capacitance of an isolated conducting pair is given by C, right? Equal to 4 pi A naught A, right? A means the radius, where A here means the radius of the sphere, and we already know 4 pi A are constant. So these are the formulas that we should note in this course. Now let's talk about the factors that affect capacitors. To talk about the factors that affect capacitor is very easy. We don't need to stress our brain too much or cram. We just need to go back to the first parallel plate capacitors, the formula for parallel plate capacitor. Recall that C, right? Remember that C is equal to K E A over D. From here we see that the capacitor is directly proportional to the area of the plate, right? Also, it is directly proportional to the thickness and dielectric. Talk about K factor here. Proportional to the thickness or dielectric and dielectric. So proportional to dielectric. Same, the capacitance of the plate proportional to the position of the plate. Position. So the first one is area, right? The second one is dielectric. The third one here is position. How does position affect this formula? D, right? The distance of their separation, how they are being positioned by distance. Are you getting it now? And the other one is the geometry of the plate. The geometry, how the plate is. Is the plate a flat plate or a round plate? Now let's talk about capacitance in series and parallel. Capacitance in series and in parallel. Capacitance in series and in parallel. So capacitance in series and parallel. So for series connection of capacitance, what is series connection of capacitance? Something like this, right? Like this. So the input of the first capacitor, the output of the first capacitor becomes the input of the second capacitor. For example, you see this is the output of the first capacitor. The second capacitor starts from here. Are we getting it now? Yes, the output of the second capacitor becomes the input of the third capacitor. So what you can use to understand the concept of series is that in series connection, the capacitors are connected by one wire without branching. There is no branching in between. You see, for example, there's nothing like this now. No, it's just one straight wire, right? Yeah, so if we call this one C1, C2, C3, the equivalent capacitor here is calculated using the formula C equals to 1 over C1 plus 1 over C2 plus 1 over C3. Where this is 1 over C, right? Where C is the equivalent capacitance. So it means the total capacitor of the capacitance. Are we getting it now? Yes, it means the total capacitors here. Are we getting it now? This is called C. The next one we'll talk about is called parallel connection. What is a parallel connection? A parallel connection is a type of connection where the capacitors are arranged, or have an arrangement of a branching wire. You know, this is the textbook explanation. This is the textbook, right? Yeah, this is the textbook illustration of parallel. But what you will see in questions will shock you. The concept is what matters. You see, this is parallel. Why? Because you see, this wire connecting this and this. Are you getting it now? They are not one wire. Just use that to get everything we'll be talking about here. So if this is C1, C2, and C3, the equivalent capacitors here is given by C equals to C1 plus C2 plus C3. So it means that you are going to add all the capacitors together, right? So let's go into energy stored in a capacitor. Energy that's stored in a capacitor. For energy stored in a capacitor, the formula used in solving energy, right? Energy stored energy stored in a capacitor is given by the first formula here is W is equals to Q C square. W is equals to Q square over 2C. The second formula we should note is 1 over 2 CV square. And the third formula is 1 all over 2 QV. In case you want to learn how to derive it, it's not hard. Remember that work is equal to QV, right? So what of work done on a small charge? That means the small work, that is the W, will be equal to what? Will be equals to V dq, right? So how do we get the work? By integrating. If we integrate dW, this will be the integral of V dq, right? Now integral of V dq. Now recall that V is equal to, remember that C is equal to Q over V, right? So from here, if you make V solve of formula, V will be equal to Q over C. Substitute Q over C in this part now. That means that the integral of dW is W, right? So W will now be equal to Q over C dq, all integrated. So if you integrate this, our only constant here will be C, that is 1 over C, the integral of Q dq. Integral Q dq is same thing as Q square, right, over 2 in the bracket of 1 over C. Are we there? Yes. So that means that W is equal to, if you rearrange this very carefully, Q times 1 is Q square, 2 times C is 2C. So this is how we got our first formula. Yeah. To get the second formula, everything still comes from this substitution. Substitute the value of C into this point, right? That is Q over V. Put it here. You will have this formula, and also substitute Q. Make use of the formula here and substitute it in this same formula. You will have this formula. Now we have a question here, right? And the question says that is example 5.1. Now, sorry, this time we are just going to be selecting some type of questions, right? Don't be wasting much time. So here it says the plate of a parallel plate capacitor are 5.0 millimeter apart in a 2.00 meter cube area. So in here the distance is 5, right? 0.0 millimeter. Immediately you are seeing this, just change it to meter, that is multiplying by 10 raised to power 3, right? Yeah, so and area is equal to 2.0 meter square. Is already in meter. So a potential difference of 1000 volts is applied. So here we have V equals to 1000 volts applied, right? Find the capacitance. So how do we find the capacitance here? How do we find the capacitance here? Recall the capacitance is equal to what? K, right? E naught, right? Area over D. But in terms of air, when there is air or vacuum, K is equal to 1. So this will reduce to E naught A over D. So we already know our E naught. Our E naught is given by 8.85 times 10 raised to power minus 11, right? Our area is 2.0 meter. All over distance of separation is 5 times 10 raised to power minus 3. If you input this into your calculator, you're going to have a value of 3.54, right? Times 10 raised to power minus 9 farad. Times 10 raised to power, 3.54 times 10 raised to power minus 9 farad. If you want to express this in picofarad, it's same thing as saying 3.4 and 10 raised to power minus 9. 10 raised to power minus 9 is same thing as 3 and 6, right? So I just take out the 6 part from it because 6 means micro. That's minus 6. Okay, that's minus 9 is minus 3, minus 3, minus 6. So this becomes 4 times 10 raised to power minus 3 microfarad, right? 5.4. Alright, let's go to the next question. The next question here we'll talk about that's option B. It says the charge on each plate. How do you get the charge? Remember that the first part we got the capacitance, right? We got the capacitance to be equals to 3.54 times 10 raised to power minus 9 farad. Now to get the charge Q, what do we do? Recall that C is equal to Q over V. Make use of the formula. Q is equal to CV, right? Yeah, so that implies what's our C? 3.54 times 10 raised to power minus 9 times 1000. Are we there now? So make 1000 solve the formula, that becomes, multiply this, you have 3.54 times 10 raised to power minus 6 coulombs. Option C here says that the magnitude of the electric field in between the space, Recall from Gauss law, we know that electric field is equal to what? area charge density over epsilon. Remember this formula, right? All right. But area charge density is equal to Q over area. So when we put it here, that becomes Q over A area, right? So our charge we got was 3.54 times 10 raised to power minus 5 all over our epsilon is 8.85 times 10 raised to power minus 12. Then we have 2 meters, right? 0.2 meters. So when you put this in your calculator, what will you have? When you input this into your calculator, what will you have? So when you have this, you will have 2.0 times 10 raised to power 6, right? 2.0 times 10 raised to power 6 Newton per coulomb. That is the electric field here. So let's go into another question, because today we are going to be solving different problems. All the problems that are involved in these calculations, we are going to be doing them right now. So I want you guys to understand the concept of energy density. Energy density, I'm not deriving, I'm giving you the formula. Energy density U is equal to 1 over 2 K epsilon E squared. This K here means the dielectric constant, right? E means permittivity, and this E here, capital letter E, means what? Means electric field. So this is the formula for calculating electric density. If we are correct, let's check a question on 5.3, example 5.3. It says, what is the magnitude of the electric field required to store electric potential energy of 2.5, right, in a vacuum of 1.3. So in here now, we can see that the energy is equal to 2.5 joules, right? And the volume is equal to 1 meter square. So energy density, you know, sometimes we explain concepts with question. Energy density, write this formula down, is equal to energy density is equal to energy stored all over volume. I want you to understand. Energy density is equal to energy stored over the volume, right? So from here now, what is our energy density? Our energy density U is equal to the energy stored, that is 2.5, over volume, that is 1, which is also 2.5 joules per millicube. This is our energy density. But what they ask us is the electric field. Now using this formula here, right, that U is equal to 1 over 2 K E square. If we make E subject of formula, that means that E will be equals to 2U, right, 2U over K epsilon, right, or in the roots. So the same thing as saying 2 times 2.5 all over K, since they said vacuum, K is 1, right, and E is 8.85 times 10 raised to power minus 11. 8.85 times 10 raised to power minus 11. Let me write it well so that we can see it clearly. 8.85 times 10 raised to power minus 11. Are we getting it now? So to press that in your calculator, what you should have is equal to 7.5 times 10 raised to power 5
volt per meter. Alright, so let's jump into some exercises here and begin to dissolve them one after the other. Let's begin to dissolve some exercises here one after the other, because it's no time anymore. Time wait for no man, but man always wait for time. So here, right, like I said, I'm not going to solve all the questions. Just going to solve the one that is hard. Alright, in same 5.3 we have option D, option B. It says if the magnitude of the field is increased by 500%, how much energy is stored per cubic meter? How much energy is stored per cubic meter? What do we do? First, we have to have a relationship between U1 and U2, right? Yeah, that's what you do in this case. Remember that U is equal to epsilon, right? Since K is 1, E squared. So in this case now, we are looking for a relationship between U and E. So these are constants. So let's just say U is equal to K epsilon squared. Make use of the formula, you know variation from primary school, right? So if you have one here, you have one here, this will be 2, right? So this is just what we are going to work with. If we have, what's our U1? Our U1 is 2.5 over, what's our E1? Our E1 is 7.5 times 10 raised to power 5. But this will be square, right? Following this formula. Will be equal to our U2. What's our U2? That's what we are looking for, right? Because they say how much energy will be stored. What's our E2? Now they said E2 increased by 500%. So that is 500% of E1. So that's 500 over 100, right? Times 7.5 times 10 raised to power 5. So this is just what we are going to put here. 500 and 500 over 100 is 5, right? So that's same thing as 5 times 7.5 times 10 raised to power 5. Now we have 7.5 here, but what we do is that we have to square it. So when we square, we make use of a formula, right? Yes, so that means that our U will now be 2.5 over 7.5 times 10 raised to power 5 square multiplied by 5 square, right? It's same thing, still the same thing as saying 5 square, yes, times 7.5 times 10 raised to power 5 all square. No space. Sorry. All square. So in here now, in here, this will cancel this and you'll be left with 2.5 times 5 square. That is same thing as 2.5 times 25. Are you getting it now? So if you evaluate this in your calculator, you have 62.50 per meter. So this is the answer. So let's dive into some exercises and see how it goes. Let's dive into some exercises here and see how it goes. So I'll just solve some tough exercises. So more detailed question in the future. So in the exercise, we have here exercise so the first one, calculate the capacitance of two plates, area of 4 cm separated by 1 millimeter. This is easy now, just use C, right, is equals to K E A over D. Area has been given as 4 cm square. Convert cm square to meter square, and distance is 1 millimeter. So substitute, you will have your answer. Okay, so we have a question here. It says a capacitor is charged by a 12-volt battery and then disconnected. It is then connected to an uncharged 3 microfarad capacitor. A 6 microfarad capacitor is charged by a 12-volt battery. Are we getting it now? And then disconnected. It is then connected to an uncharged 3 microfarad capacitor. What is the final potential difference between each capacitor? This is very easy, right? So first, there is something you are looking for. From this capacitor here, they say the 6 microfarad capacitor, that is 6 times 10 raised to the power minus 6 capacitor, was connected to a 12-volt battery, right? So our V is 12 volts. Then disconnected. So from here, recall that C is equals to Q over V. So let's find the charge that was stored in this capacitor. So the charge that was stored, Q will be CV, right? Which is the same thing as 6 times 10 raised to the power minus 6 times 12. So when you press that in your calculator, 6 times 10 raised to the power 6 times 12, you will have 7.2 times 10 raised to the power minus 5 coulomb. Now, when it's now discharged, this 6 ohm capacitor, sorry, this 6 microfarad capacitor will have this charge. Are we getting it now? When it's now connected, now in this case now, Q here, this is the logic that we use in solving questions. See, we now have Q. Now, this charge now, they say that the capacitor, this 6 farad capacitor, is now connected. So let's do something like this. Let's say these are the capacitors, right? Just an illustration. So this is the 6 microfarad capacitor. It's now connected to the 3 microfarad capacitor. You see, now this type of connection is a parallel connection. Note that, because each ends are connected, right? How does parallel connection is? This is the end, first terminal connected to, are you getting it now? Yes, the end of each end are connected. 1, 2, 1, 2. This is a parallel connection, right? And the total capacitance in the parallel connection is given by C is equals to C1 plus C2. So since there are just two capacitors here, the total capacitance here will be equals to 6 plus 3, that is equals to 9 microfarad, right? So we same thing as 9 times 10 raised to the power minus 6 farad. So that is our C. So recall that C is equals to Q over V, right? So what will be V? V will now be equals to QC. That is, what is Q? 7.2 times 10 raised to the power minus 5. Then what is C? 9 times 10 raised to the power minus 6. If you plug this in your calculator, you will have 8 volts. Alright. We have a question here. I think this is very easy. This is easy enough. This is exercise The exercise we just did just now is exercise 5.2. Exercise 5.3 here, let's just quickly break it down. This is what we call my exercise 5.3. It says that capacitor G is equal to 5 microfarad. Sorry, capacitor C1 is equal to 5 microfarad and C2 is equal to 8 microfarad. It says they are connected in series to a 9-volt battery. How much energy do they store? Very easy. So in this case now, what they just gave us is capacitor, that is capacitance and voltage. So we have three formulas. The first one is what? Q square over 2C. The second one is 1 over 2 CV square. Without going further, we have already known that the second formula is what we use because it has only capacitor, right? Yeah, because it has only capacitance and voltage. So in that case now, we will use this W to be equal to 1 over 2 CV square. But what's our C? Our C now is, they say they are arranged in series. So our C will be given, to get our C will be given using 1 over C, right? It's equal to 1 over C1 plus 1 over C2. If I'm not wrong, then that means that this is the same thing as saying 1 all over 5 plus 1 over 8, right? You write your press that in your calculator, no time to be doing fraction. Those are for primary school children. So you have 1 over C as 0.325. So invert this side now, right? When you invert this side, this side will be, I will see the 1 over 0.325. So that will be equal to 3.07. So that's our C, right? So since we have C, we can plug into this formula to say that our energy stored, that is W, equals to 1 over 2 times 3.07 times 9 squared plus 9 is equal to. So if you press this in your calculator, you have 124.6 joules, right? Yes, or if you divide through, that's your answer, or 125 joules approximately. That's your answer. So I think 5.4 and 5.5 are simple enough. Thank you very much for watching. In next class, we are going to be going to dielectrics, straight to solving questions here.